principles of quantum weirdness, which is kind of a little ambitious topic because it's not usually the kind of thing that we talk about here on Fermilab. Our science is kind of on a different level than the fundamentals of quantum mechanics, which is what I'm going to talk about today. So it's a little ambitious, but it's a very fun subject. So for any questions, please put them in the chat, and Amanda, please interrupt me. So in this talk, I will explore some of the most fundamental and weirdest things that we know about how our universe, how our reality works. And I will try to make the connection between that very fundamental science to the kind of experiments that we do here in Fermilab. And as you heard from Amanda, I work on the mu-2 and the mu2e experiments. So these are specifically experiments that I will be making the connection to, and the precision frontier kind of physics research specifically, or a little more broadly. And since some of the fundamentals of quantum mechanics is a very popular topic, and there's a lot of content out there for you to explore. There are professionals that have done some really nice animations, and I'll be using some of those from a couple of nice YouTube channels. And this is the PBS Spacetime and Arvin Ash. So for anything more, for more details, you can look into their videos. So this is one of my main points for the talk today, and I hope to convince you that this universe that we find ourselves in is pretty weird. And what we know about so far leaves many questions open and unanswered that could have amazing implications. And a very good experiment to demonstrate this is the double-slit experiment. You might have heard about this in school. This is a very old experiment. It was performed more than, at its most fundamental form, more than 2 centuries ago. But it's a great tool to let us dig into some very deep truths about our universe. So fundamentally, the experiment is just a light source, and then the light goes through 2 slits in a metal, 2 openings through a wall. And then looking at the screen on the other side of the 2 slits, we see an interference pattern. And that is, you probably know already that this is a very common behavior that we associate with waves. So we already knew even 2 centuries ago that waves work like that. That experiment showed us that light actually behaves like a wave. So this familiar wave behavior, and this is a very nice animation of this. So light as wave hits the 2 slits. And on the other side, now the 2 slits act as 2 new sources of light waves. And in different regions here, these 2 new sources interfere constructively and destructively. At points where the high of one source meets the high of another source, we have constructive interference, and at the opposite, we have destructive interference. So the result that we see on the screen, this interference pattern of highs and lows, is the sum from both paths, from both slits. So this is something that we've known for a long time, that light actually behaves like a wave. Getting a little more interesting is that not just light, which we now know we associate with a massless carrier of light or a particle of light, but particles that have mass, fundamental particles like electrons and even heavier particles, also behave like waves. So if we replace the light source with an electron source, a source of fundamental particles, and through the double slit, now on the other side, we again see an interference pattern. And that is what we call a duality between the wave and particle description. So electrons and other fundamental particles behave both like particles and like waves. And we'll get a little bit more into that in a bit. Now, what is even weirder is that the previous picture worked for an electron source. So the assumption was that electrons go through both slits, and there is an interference from electrons coming from both slits, and that creates the interference pattern on the screen on the other side. But it turns out that even if we send only one electron at a time, what we will see is that each electron will be recorded on the other side, but in the end, after we repeat that over and over, we see an interference pattern forming again, which means that this interference pattern must mean that now the electron or any particle must go through both slits itself and interfere with itself. So every single particle goes through both slits effectively and interferes with itself. So again, like before, one particle alone will take all possible paths available to it, and the result on the other side is the sum from both paths, or the interference. And in fact, it doesn't have to be just two openings. It could be 1,000 or more. The particle would go through every one of them. The particle will take all possible paths, and the sum of what we see on the other side is the sum from every possible path. Now, not every path has the same probability. So something that the particle will have to go a long way out, it has a lot less probability than a more probable path. But the result of what we see on the other side is the sum of all possible paths. So a very succinct way of saying that I think encapsulates the issue very well is that everything that can happen happens. If you give the particle 1,000 openings, it will go through all of them. Not with the same probability, but it will go through all of them. And in fact, you can think about it as all these different paths. What if there were more than 1,000 openings? What if there was an infinite number of openings? So an infinite number of openings is the same as completely removing this entire wall in between. So even if there's no wall, there's an infinity of paths that the particle can take and will take. And the result on the other side is the sum from all these possible paths. So this might sound getting a little weird and crazy, especially if you think of a particle as, a single entity. If you think of it as a tennis ball, for example. But this is not crazy behavior if we think about it completely as a wave. So think about this experiment being performed on the surface of a lake, for example. And there is a wave on the surface of a lake propagating, and the wave will go through every one of these slits. That's fine. So this behavior is still okay if you just accept that the fundamental particle is just a wave. So every particle behaves like a wave fundamentally. So okay, that's very weird, but at least that's a good rule. And if that's how it works, then okay. So what's the problem with that? The problem is that, if everything is fundamentally a wave, then where are all the waves in our everyday life? So the world of our experience, what we call the classical world, is all like particles. So if we were to run the two slits experiment again, but now with tennis balls, so now we have a tennis ball launcher doing the experiment. Now, well, we don't get interference. Tennis balls do not behave like waves. This is not surprising. We know that. So this is why particle wave duality is kind of a mystery. We don't know what it means fundamentally. But Particles at the very fundamental level behave like waves, but at some point they start behaving like particles again. At some point between the electron or the particle of light behaving exactly like a wave, all the way to tennis balls, there's a boundary somewhere there between particle and wave behavior. And it turns out that this boundary is exactly when we make a measurement. So if we want to run the exact same experiment as before with the electron source, so now sending electrons through a double slit as before, where we got an interference before. But now if we put in a detector and we try to answer the question, well, an electron should not go through both holes, or if it does, let's try to answer the question, which one does it go through? So now if we run the experiment again, throwing electrons, now we don't get an interference pattern. So it seems to be the measurement that collapses the wave behavior into particle behavior. So now electrons will act exactly like tennis balls. And if you think about it, the picture that I showed before, even when there was interference emerging when we sent electrons through the double slits, so the electron was behaving like a wave and interfering with itself. But when at the point of actually making the detection on the other side, we always have just one electron going splat on the detector. And at that point, the electron that was a wave that interfered with itself behaved like a particle again when it was measured on the other side. So the only difference is that here we make the measurement earlier and we turn the electron into a particle again, like a tennis ball earlier. So this is what we call in physics as wave function collapse. Again, this collapse of wave behavior into particle behavior. And I will come back to say a little bit more about what the wave function is. But there seems to be something specific about when we make a measurement. And now this is getting really weird. So why would making a measurement be something special? Why would it matter? So that seems to be a huge distinction about particles behaving like waves and particles behaving like tennis balls. So it's a huge boundary, this measurement. And what is a measurement anyway? So putting a screen on the other side and the electron goes splat, apparently that's a measurement. But what is it about the detector? Something that is very characteristic about how incredibly weird that is that people have legitimately proposed that maybe it's interaction with our consciousness that forms a measurement. When we become conscious of that interaction, that's when this collapse occurs. Now, I don't think that's true, but something weird is certainly going on. So what is the difference and when does that jump occurs between that quantum world and tennis balls, basically? And I'm sure you heard about the Schrodinger's cat experiment. So it's basically a quantum experiment that basically says, the equivalent of going through the two slits. If you go through the top slit, let's say, then the cat lives, and if you go through the bottom slit, then the cat dies. And it's very cruel. I don't know why the cat has to die, but I don't think anyone has ever heard a cat trying to answer that question. But this is a very nice thought experiment that especially illustrates the weirdness of trying to connect this quantum mechanical unanswered questions to our everyday experience. So, you can think of, well, it doesn't matter in our experience, in our everyday life, which slit the particle will go through. But with an experiment like that, you could imagine that it would. So so now it starts to get personal. Now we start to think about how does that affect our own experience. So I mentioned the wave function before. It's a term that you probably heard before. So basically, this is I could claim that this is a wave function of the double-slit system. And I'm using some physicist notation here, so try not to worry too much about it. So this term on the left is one state of the system where the particle goes through the top opening, let's say. And this term on the right is the other state of the system where the particle goes through the bottom opening. So this is the wave function of the double-slit system. The particle will go either through the top opening or through the bottom. These are the only two available choices. And they are described by these two terms in, let's say, this object that is the wave function of the system. Now, we should add to the wave function the observer too. Now we are the observer. It's a pretty interesting move in itself to admit that we as an observer, we are part of the system. And the observer doesn't see, in the case where there is interference between the two slits, the observer doesn't see any difference between the two holes. Doesn't differentiate the two states. What we see is the sum between the two. Again, the interference is the sum between going through the top opening or going through the bottom one. So the observer just only sees the sum of the two in the parentheses here. We call this that the system is on a superposition. So basically the particle goes through both holes, and that is what we call the superposition of the two states. And the observer sees the sum of these two states. Now, as we saw, so when we try to ask the question exactly which path does the particle take, now we only see one outcome. So now let's say that we saw the particle go through the top opening. So now the system collapses into just the particle going through the top opening because that's the only thing we see. And now our state, the observer state in the system, is that we see the particle go through that opening. It's a suggestive way of putting this, and everything here is kind of open to interpretation. Everything that I show here, and this is so weird that there are many different interpretations that are all valid, that could all be truth. And in fact, even some choices that I make in how I describe the system here, already there are physicists that would think, well, I don't like that interpretation. You're making an interpretation here, and I don't like it. And that's how weird it is. Physicists don't agree about how this is interpreted, what it all means. So keep that in mind, that there are some choices made here, but everything that I say here is consistent with the experiments as I described. So this is the collapse of the wave function that I described before. We ask the question, which path does the particle go through? We only see one path now, or the electron only goes through one path, and we see that as a result on the other screen. There's no more sum, there's no more interference, and we see the electron going through that path. So to say that, to elaborate on that, is that what happened here when we asked which path did the particle go through, and we saw the particle go through the other path, there is a whole other branch, let's say, of the wave function, the particle going through the bottom opening, that should also exist, but it has completely disappeared. So, like I said, when we ask which path does the particle take, we only see one path. That's the one path we see, and Even though before we asked that question, the particle went through both holes, it doesn't anymore. So the other opening, the other path, is just disappeared. And that is what the wave function collapse, that's how it works. We don't really know what that means, like I said, but we know that it works. If we take that description and we use quantum mechanics based on that, there's an amazing wealth of things that we can accomplish, and we have. We have built our entire society based on that description. But how that works fundamentally, we still don't know, basically, and it's open to interpretation. And one interpretation of this that I think is very fun and interesting is that, we see the particle go through the top opening in our world, but everything that can happen happens. These are the rules that we know quantum mechanics obey already. So seeing the particle going through the other path could also be happening. In a way, this is a much more pure and economical description, because in the description before, we had to impose new rules. We had to completely destroy this part of the wave function. And there's no really justification for doing that, just that it matches experiment. But rather than imposing new rules, we could just say, this is our world, and in our world, we see the particle go through the top opening. And then in another world, I guess, we, or another version of us, observe the particle go through the bottom opening. And that also happens. So that is what is called the many worlds interpretation. This sounds very fringe and sounds very crazy, but it is arguably the more pure and the more straightforward interpretation, as I described it up to now. It doesn't impose any new rules. In fact, the fundamental shift in the description in this interpretation is not directly that there are many, many worlds, but the wave function is, we should think of the wave function not of the particle itself, not of the double slit system, but of the entire universe is in a wave function, that everything is part of the system. And then in this branch of the wave function, this is our universe, and then our world, and then this branch of the wave function also exists. It just has to be a different universe. And like I said, this is just one of few interpretations. And as crazy as it sounds, it's a pretty good one because of how economical it is. There are a lot of physicists that actually like it very much. But of course, it creates a lot of questions. This is our world. This is our universe. So now we have to think about. So there are infinite copies of us, or is it infinite? That's an open question in this interpretation. If whether it's an infinite amount of copies or just many, 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 many copies, many copies of what happened to the particle going through the slit, and many copies of the Schrodinger's cat, and many copies of ourselves. So there are a great many number of questions that arise from that. But this is how weird quantum mechanics is, that this is one of the most reasonable and accepted hypotheses.
You do have a question in the chat if you have a second.
Sure.
So Brian asks, I'd like to know if and how quantum weirdness might relate to the multidimensionness of the universe beyond the four we ordinarily perceive.
That's a great question. So it very well could. The answer is we don't know. But there is a lot about quantum weirdness that could relate very much with open questions about gravity. And I haven't included anything about gravity in this talk because it's not my work. It doesn't have to do with most of the experiments in accelerator science in Fermilab. But a lot of these open and unanswered questions could very well relate with a lot of open and unanswered questions in gravity. And gravity, gravity kind of is space-time. So your question about dimensions of space-time is really a question about gravity. And some very interesting terms that are very relevant here are entanglement, perhaps, which I will talk about in a second because it is very important. I want to touch on it. And locality is another term. So these are some very important concepts that could relate all this kind of weirdness to questions about gravity and dimensionality of space-time. And in fact, so I talked about you know splitting the universe, and in fact, there's an app for that, and you can split your own universe. There's an app that you can install, and it connects with a quantum measurement device in CERN, in a lab in Europe, and that device will make a quantum measurement that is the equivalent, let's say, of the particle going through both slits. And then you can make your choice based on that. You can choose to, based on this measurement, I will either cook my own food tonight or I will order pizza. So you can split your own universe based on a quantum measurement. So in a way, this is a much more straightforward way of getting to the question of how does this quantum weirdness affect our own life than the Schrodinger's cat thought experiment does. So I'm not really an expert on this. I do experimental physics. I don't work on the fundamentals of quantum mechanics. I would point you to Sean Carroll's work. He has an awesome book out, and he has a podcast and a lot of work that you can find online. He describes many worlds on a lot of a great depth, and in fact, he goes a lot into connections with gravity, which was like the question that I just got. And as like I said, I don't work in this. I'm not an expert in this, but it's very interesting to hear about it. And as a physicist, I'm convinced, at least by the argument, that this is one of the most beautiful and straightforward interpretations of how it all works. All right, so moving forward, after having casually talked about many worlds, so fundamental particles have a property called spin. So you can think about it as, if a particle was like a tennis ball, then a spin would mean rotation. And it makes sense then that this property relates to an interaction of a particle with a magnetic field. Because just like in a classical world, if you know your electromagnetism a little bit, a spinning charge is equivalent to basically a little magnet. So it makes sense that this property relates to interaction with a magnetic field. And you can ask the question, so now this wave function of the particle's spin state, if we ask the question specifically about the direction in the vertical direction, the particle can have a spin either up or down if we make the measurement like that. And the wave function, then you can describe it exactly like the wave function that we described for the double-slit experiment. So everything that we've learned there, we can take it in investigating the particle's spin. Spin is conserved in a system. So if we think of, let's say, a parent particle with spin 0, then if it decays into two particles, then these particles must have opposite spin. So if we measure the spin in the horizontal direction, then the particles will have spin opposite in the horizontal. If we measure it in the vertical, they will have opposite spins in the vertical direction. So I wanted to touch on entanglement because it is a really interesting and fundamental concept. So what I described here, these particles must have opposite spin. This is basically what entangled particles are. So these decay particles are created and they are connected. Their spins have to be opposite, and that's what entanglement is. So this nice little animation. The particles are created and the spins are created in opposite states. But as far as we know, every one of these particles, their spin is allowed to be in any possible direction. So for any one of these particles, the spin is on a superposition of states. So this is a particle with a spin in all directions on a superposition. And now we as an observer, we observe and we measure the spin of one of these particles. And we measure the spin in this direction. It comes out in a random direction. And when we measure one, because they are entangled, the other particle is necessarily determined. So the spin of the other particle must be opposite to the one that we just measured. Even if we don't measure that, or if we measured it, or if we go and measure it afterwards, then we know what the answer will be just by measuring this one. That is what entanglement is. So some questions arise about what does that mean and how it works. So again, the two particles are created and they are entangled. So their spins are created opposite to begin with. We know that. That's what entanglement means. We allow them to move far apart. Each one is in a superposition of all possible spin states, as far as we know. But they're still entangled together. The connection between them remains. And now we observe one and we collapse its wave function. So observer Alice observes the particle and observes the spin in this direction. So it collapses the wave function of this particle and presumably the entire system. So assuming that the system includes both particles. So now in an experiment, what if we collapse the wave function of this particle, but this particle is too far apart for information, even traveling on the speed of light, to reach it. And then we determine the spin of this particle before information has time to reach us from the other observation. And what do we see? So observer B, let's say Bob, even though information from this measurement doesn't have time to reach us, even traveling on the speed of light, Bob will see that the spin will have the direction that we would expect if we knew the result of this measurement. So what does that mean? Does that mean that information from this measurement traveled faster than the speed of light to reach this particle? That is really, really problematic. Faster than light travel is really, really a big no-no. It would violate causality. It would mean that we can travel backwards in time. We really don't think that this is possible. So, so what gives? What's going on? So Einstein called this spooky action at a distance. You might have heard the term. So for many, many decades now, since the very beginnings of the quantum mechanics, these questions have been open from the very beginning. And understanding of how it works is not complete. The question here in this paper by Einstein and colleagues poses the question very well. Can this quantum mechanical description, the basic description of how it works and how we can do calculations based on that, is it complete? Questions like the one posed here, how can information travel faster than the speed of light, are not answered. We don't know how it all works. And again, there are different interpretations. And I should say that Einstein, Podolsky, and Rosen were exactly the ones that formed this thought experiment. So this exact thought experiment that we're dealing with here was posed 85 years earlier. So these questions have existed since the foundations of quantum mechanics, and they're still open. Is there a question, Amanda? I would take it now.
Yes, it says, Joe asks, perhaps do you collapse the wave function by observing the state of the parent particle?
That's right. Well, we do collapse the wave function. So like I said, the particle, this particle on the left, was on a superposition of all possible spin directions, and then we collapsed the wave function. So the wave function of the particle is collapsed. So it's a very good question, and the question kind of becomes, what is the wave function, or what is the proper system described by the wave function? If you think of, this wave function, this particle has one wave function, and this other particle has a different wave function, then you have to assume that information traveled faster than the speed of light to reach it, which doesn't happen, can't happen. So this really can't be a correct description. So you have to think of what is the right wave function to think in terms of. And like I said, in the many worlds interpretation, the proper system to consider is the entire universe. So in the many worlds interpretation, this is easily interpreted. When we measured this particle, we collapsed the wave function of the entire universe. Therefore, immediately this particle has the spin direction that it does in this universe, in our universe. And there is no ambiguity. There is no travel faster than light. There is no information that has to be propagated. In this universe, this is the direction of the spin of this particle. And there are an infinite other number of universes in which the spin of the two particles are in a different direction. So it's a great question. It is one of the right questions to be asking to get at the truth of what's going on. So again, that was just one interpretation, but that is one way to resolve. Information traveling faster than the speed of light is basically crazy. It doesn't happen. It's not a valid answer. So having many worlds and infinite copies of you sounds crazy, but in fact it is. It describes observation perhaps much more logically than many other interpretations. And again, that's just a demonstration of how weird everything that we know about quantum mechanics is. Was there another question?
There was another follow-up. How is the wave function of one particle influencing the wave function of an entire universe?
That's a great question. Well, these two particles are entangled by creation, so they are connected. So are we connected? Is Alice as an observer connected with this particle? Yes, they are. You can argue that entanglement is the measurement that we said before. So the measurement having a very elevated significance in this description, measurement is exactly the tool that makes us entangled with this universe that has this spin direction. And what is measurement? You interacting with the particles of air around you. Every time one of your molecules interacts with a molecule of air around you, this interaction, you can call this a form of measurement or a form of entanglement. Again, this is all interpretation, but this is one way to think about how the entire universe is basically an entangled entity. And all these many universes and many worlds are in a superposition between them. There was another question.
Yes. So if there are multiple realities, are they fixed or constantly being created based on choices and decisions we make or some other factor?
That is a great question. We don't know. We can only know our own universe, which sometimes sometimes our universe is in a superposition of many underlying universes, and sometimes we split into we collapse into a universe, and there's a very large or infinite amount of universes that are separated from us. And every time there is a measurement, this is what happens. And again, every time that one of your molecules interacts with an air molecule, this could be happening. Or maybe that's not accurate. It could be that every time there is something more quantum, let's say, like radioactive decay is a quantum property. So the Schrödinger's cat experiment relies on that. It relies on a radioactive decay as the superposition. So just in our body, there are thousands and thousands of radioactive decays going on every second or so. So maybe that's a count. That's an accurate count of how many of these splits happen. Maybe just from our radioactive decays, there are thousands and thousands for every second for every person. And there's a good chance there's many more than that. Again, just an interpretation, but it's so interesting that it's fun to think about. Any other question?
One was more of a response to the one before that. Do you want to hear that? Or it says, in response to the previous question, I believe the multiple realities worlds are continuously splitting off and not related to our decisions, but the decoherence happens at a quantum level.
Yes, that's right. That is what I described basically. Thank you. That sounds right. But if you wanna be part of the game, download that app and you can split your own universes, and you can ask more concerning questions about what are the implications of splitting the universes. Maybe you can think about it as the more universes we create, the more life you give, the more of you and the more humans you create. So maybe the most moral thing you can do is to click that app as many times as possible and do as many quantum interactions as possible. Any other question?
Are you suggesting that after the Big Bang, as different particles were created, entanglement started affecting all the particles in some way or the other?
So in this interpretation, I'm not suggesting that. I'm comfortable living my life in uncertainty about what's going on. But this is a kind of a beautiful interpretation in how economically it solves a lot of open questions. And in this interpretation, the entire universe is entangled, and entangled and in many superpositions. So with every particle whose spin has not been measured, there is a superposition of potentially infinite universes. So our entire universe wave function is entangled every single moment, and there are many, many superpositions within that entanglement waiting to be collapsed and separated. All right. Shall we move on to?
Yes, we can follow up with the ones at another kind of
All
natural
right.
pause.
So I hope I convinced you that the quantum world is very, very weird. So weird that this interpretation that I'm providing is one of the most reasonable ones, perhaps. Um, but weird as it is, not clear as we are on its interpretation and how it all works, what it all means. Quantum mechanics is definitely triumphant. It is excellent. It works amazingly well. Uh, Again, we can't quite interpret what these measurements mean, but they definitely work. So these radioactive decays that I said are a quantum mechanical phenomenon, and without them, the sun wouldn't burn. And perhaps more importantly for us than the sun, okay, not really. We have built a lot of technology based on quantum mechanics, such as semiconductors and transistors, on which we have built our entire modern society. So as weird as it seems, we have harnessed the power of quantum mechanics to build our modern society. And we have harnessed that power, and we've done experiments based on our understanding of quantum mechanics, and certainly using technology based on quantum mechanics to build our understanding of how what is the particle content in the universe and what are the interactions between them. This is what we call the standard model. It is an incredibly successful theory. It describes very well the world around us. The last particle that it predicted, the Higgs boson, was discovered in 2012. That was the last particle predicted by the standard model. It was discovered right about where we thought a very reasonable place for it would be. So the discovery was really a crowning triumph for the standard model. And it describes three fundamental interactions or forces: electromagnetism, strong nuclear force, and weak force. And again, it has been so successful, standing up to experiment over many decades, such that we call that sometime our theory of almost everything. And even though it has been so successful, the standard model as a theory cannot be complete. The easiest way to say that is that everything that we know, all our universe that we know of, lives here in this tiny slice of what we have measurements to think that the matter and energy content of the universe is. So our understanding of what the standard model describes is less than 5% of everything that we know of. So the universe is a lot more vast than the universe describes, than the standard model describes. And we need to look for new physics beyond what's described in the standard model. So the most direct way to do it, and I say, discovering new physics means discovering new particles or new interactions outside of what is described in the standard model. So the most direct way to do it is to build gigantic machines like the CERN Large Hadron Collider in Switzerland and France, which is operating right now, or the Tevatron collider that existed in Fermilab until less than a decade ago. And these giant machines is what is needed to accelerate particles so much, so close to the speed of light, and give them so much energy, and then collide them to create enough available energy to directly excite matter into new forms that we hadn't discovered before. So by directly creating enough energy available to create the Higgs boson, like I said before, at its energy of 125 giga electron volts, 125 GeV. And what this unit of energy means is not that important. Just think that we need a giant machine to accelerate it so much, accelerate particles so much, and then collide them. And that is what we need to have enough energy to create the Higgs boson. So just keep that in mind, what that stands for, and I will come back to that in the end. So this is, again, notice emphasis on directly creating new matter and directly having enough energy available. So a complementary approach to doing that, which is perhaps more and more important as there is no new physics coming out of the LHC or the Tevatron yet, no physics beyond the standard model, is at what we call the precision frontier. So in this approach, we measure something very, very precisely. And the goal is to detect a difference from what the standard model predicts. And that difference could be coming from an indirect effect of new particles and new interactions. So big giant machines directly create enough energy to directly see new matter. And by measuring something to very, very high precision, we can indirectly see an effect from a new particle or a new interaction. And the muon G-2 experiment, which I will talk a little bit about in the slides coming up, is basically a very high precision measurement. So you can think of it as a giant microscope to measure something very, very precisely. And in this approach, indirectly, we could actually access energies that are more than 1,000 times higher that are directly accessible at LHC. All right, so to see how the precision frontier works, let me go back to giving you some more weirdness in quantum mechanics. Let me talk about the uncertainty principle, or let me introduce it briefly. So the uncertainty principle is that you can know both the position and the momentum of the particle at the same time. And this is, you can see here an animation of the wave function of a particle, where here the momentum is known to high precision, and now the position is known to high precision, but that means that the momentum is known less. So there's a fundamental uncertainty built into the wave function that you can know both to very high precision. A corollary to the position and momentum relation is energy and time. So you can know both energy and time very, very precisely. And because of that, some very weird things are allowed to happen if they only happen for a very short time. An example of that is quantum tunneling. You might have heard about this before. So in this animation here, what you see here is the wave function of a particle inside a wall or inside a well, which can be a particle inside a nucleus. And whereas in classical physics, this particle would have zero probability of being inside a forbidden area, in quantum mechanics, that probability is not zero. And in fact, there is some probability that the particle will escape this barrier, which if you think about it as a nucleus, then this particle escaping is basically a decay of an atom. And in fact, this is so one of the processes that I said before, how that could happen to why quantum mechanics is needed for the sun to burn. This radioactive decay that needs quantum mechanics to happen is one of the ingredients that are needed in the nuclear processes in the core of the sun. So this is what we call quantum tunneling. You might have heard about this before. And given that uncertainty principle on energy and time, even conservation of energy can be violated very briefly. And conservation of energy is one of our most fundamental rules of physics, but it is allowed to be violated very, very briefly. And that is what gives rise to quantum fluctuations. So particles and antiparticles can be created and annihilated together very, very briefly. You might think of it as particles fluctuating in and out of existence. That is something that can happen even in a vacuum. So even in the absence of other particles, what you see here is a computer simulation, excuse me, a computer simulation of these quantum fluctuations in an empty box. And you can think about it as bubbles in a foam of soda. And you might have heard of quantum fluctuations referred to sometimes as quantum foam. And this is some physicist ways of describing these interactions. So particles jumping out of the vacuum and with their antiparticles just appearing and disappearing, annihilating. And in fact, these diagrams here can modify interactions of particles as we know them. So here's one example of how this could happen. So how this particles jumping out of existence, in and out of existence. So for example, negative and positive particles, particles and their antiparticles are jumping in and out all the time. And for example, if we try to measure the charge of just an electron, then we have to measure it with the test charge some distance away. And what we find is that the charge of the electron, if we measure it with respect to the distance, this distance from the test charge, we find that it is not constant, but it depends on that distance. And the reason why is exactly because of the modification induced by these quantum loops. So the closer and closer we get, or the higher and higher in energy, the effect of these quantum fluctuations becomes more and more important. And the closer it gets in energy, the electron charge appears higher. And another way to say that is, you might have heard of the fine structure constant. This is a fundamental parameter in the standard model. And it too is basically not a constant, but what we call a constant is measured at large distances or low energies. So even our most fundamental constants are not really constants, and that is an effect of quantum fluctuations. And instead, we have this dependence of their values on distance and energy of the measurement. So really weird stuff continuing. And you see how all this is affecting our experimental measurements. Another example is, you might have heard of a proton. I should have made it clear here that this is a proton. It's made up of 3 quarks. You might have heard about this. In fact, this was first discovered in a measurement of the proton's magnetic moment, or G minus 2. So we call it G minus 2 because this G factor is expected to be equal to 2 if the particle is fundamental, if it doesn't have substructure. So for the proton, when that measurement was made, we found something very different from 2. We found a value of 5.6 or so. And that reveals the proton substructure, that the proton is made up of quarks. That was the first discovery and the first suggestion of quarks. But in reality, there is even more than the naive description of the proton just made up of these 3 quarks. In fact, there are much more stuff that is appearing through these quantum fluctuations inside the proton. And in fact, when we estimate the mass of these just 3 quarks, it's very, very small compared to the mass of the proton. So most of the mass of the proton actually comes from these quantum fluctuations. So these quantum fluctuations that are very, very weird, and they are allowed to do some really weird stuff. In fact, they are responsible for most of the mass of the nucleons, the proton and the neutron, and therefore most of the mass in the world that we know about, not including dark matter. All right, so how does that, so now we come to the G minus 2 of the muon. Like I said, I guess I haven't made the connection with the G minus 2 factor and spin, but the G minus 2 relates to the spin, like and interaction with a magnetic field. That's why we call it relating to a magnetic moment. So the G minus 2 factor describes the interaction of a muon with a magnetic field. And like I said before, for a fundamental particle, which we know the muon is, unlike the proton, we should get exactly a G value of equal to 2. So this is what is shown here. The G factor of the muon is describing an interaction of the muon with a magnetic field. This is what this interaction means, basically. And we expect that value to be exactly 2. But like I said, we should expect that quantum loops should modify the value of the G factor. So here is just one particle appearing in the vacuum, and it's basically like a completely different path, like one extra opening up, one extra slit opening up. So it is an extra path for the interaction to occur. So we should expect the result to be the sum of both available paths. You see that the modification is very small. It's not like the proton that it was 5.6. It is almost an order of 1,000 smaller than the main interaction. But that is an extra path, and it exists. And in fact, the interaction can take all possible paths. So everything that can happen, happens. And there is a very, very large, perhaps infinite amount of quantum fluctuations that can happen. Particles and antiparticles jumping out of the vacuum and then annihilating again. These are the vacuum fluctuations. So every diagram here is basically describing an extra opening, an extra slit, an extra path for the interaction to occur. And like we described in the double-slit experiment, the final result, the final prediction for the G factor should be the sum or the interference of all possible paths. So we should sum up all of these diagrams to get the answer for the G factor. And in fact, there are many, many paths available. So, so just looking into what we call the 10th order. So this is, there are first order and second order. So this is just the 10th order ways that this can happen. This is only in one part of the theory. And there are tens of thousands of diagrams calculated of very, very high complexity, as you see here. Fortunately, electromagnetism is pretty easy because the more complicated it gets, the less effect this extra path has. So we don't care. The more complicated it is, the less we care about it. That's great. That's what we want. And in fact, there are every known part of the theory in the standard model contributes a modification through quantum loops to the value of G minus 2. So from quantum electrodynamics or electromagnetism, quantum chromodynamics or the strong interaction, and the weak interaction. This is just a tiny example of all the available paths. Like I said, there are tens and tens of thousands of available paths. And we have to calculate every single one of them to get the expectation value for what G minus 2 should be in the standard model. So this is the theory prediction. So like I said, the theory at the most naive level expects this G factor to be equal to 2. This is coming from what is called the Dirac equation. You don't have to worry too much about it. This is basically Paul Dirac wrote down this equation and integrated quantum mechanics with Albert Einstein's relativity. Now, if we add the corrections from quantum electrodynamics, so this is gives rise to electricity and magnetism and the entirety of chemistry, basically. That's not quite true. This modifies the expectation value by some amount, where most of the effect comes from this diagram that I showed before. Most of the modification comes from just this interaction. We add the effect of quantum chromodynamics. This is the strong force that binds together nuclei. And finally, an extra small modification coming from the electroweak force, which is responsible for radioactive decays. So summing all that up, you see the level of precision in all these calculations. It's at an astounding level of something like 11 or 12 significant digits calculated in every part of the theory to incredible precision. So this is really another triumph for the standard model, this very, very precise calculation of the G factor. But the problem is that this prediction of the standard model, all this value of the G factor comes into this theoretical prediction, which is given here by some value plus minus some uncertainty. And you see that when we tried to measure that value experimentally, they came out to be very significantly different. The statistical measure of how significant this difference is 3.6 standard deviations if you're mathematically inclined. But you can see even by eye that they seem pretty different. And this is something that is very important to the entire physics community in searching for physics beyond the standard model. Asking the question, what is going on? Why is our theory different from what we measure in experiment? So what could be going on? The answer is that anything that can happen happens. So we calculated everything that we know about in the standard model, everything, every particle and every interaction that we know about, but there could also be particles and interactions that we don't know about. And if these existed, and these are just a few examples of just hypothesized new particles that could exist and could add extra paths, extra slits in the openings, more paths for this interaction to occur, that would modify the value that we should get for the G factor. So that discrepancy between experiment and theory could be a sign of new physics arising because of new openings in the wall of the double-slit experiment. So that is the motivation for the muon G-2 experiment at Fermilab. This experiment will measure that G-2 factor again and much more precisely. So hopefully we will know for sure if that discrepancy is because of new physics or not. Well, as much as we can know something for sure epistemologically. But because of the significance of that discrepancy in the global physics community, this is one of the most exciting measurements in the world. And everyone in physics is very anxiously waiting what the result will be. And in fact, a first result will be available in just a few months, hopefully. So it's a very exciting and important experiment. And Anna will give you a virtual tour in just a little bit after this talk. And I don't have time to go into the mu2e experiment, but I will just mention that this experiment is another precision measurement in Fermilab. It is also very highly and very well motivated. And just to give you an idea, this is the level of sensitivity that the mu2e has. The horizontal axis here, you can think of it as the kind of new physics that the experiment accesses. And the vertical axis is how much energy is it sensitive to. And the axis here is in units of tera electron volts. And you can see that it reaches 10,000 tera electron volts, which is basically 10 million giga electron volts. So compare that to 125 giga electron volts for the Higgs at the LHC. So just to demonstrate what I said before, that indirectly we can reach much higher and much further into being sensitive to new physics. The bargain that we do is that first of all, this factor relates to a very specialized kind of new physics. Specifically, this assumes that the new physics doesn't care about muons and electrons. So if the new physics interacts with a muon, then what comes out at the other end could be muon or electron with the same probability, which is kind of, improbable. We shouldn't expect that. So this is kind of a naive expectation, but for something so specialized, this is really how much higher we can reach something indirectly as compared to a direct measurement. And there's another side to that with the precision frontier. So this is the problem with indirect measurements, much like the G-2 discrepancy that I showed. If indeed we see a signal, so if indeed we see a discrepancy between theory and experiment, we won't be sure what it is. Like when we see the Higgs boson at the LHC, we know what its mass is, we know where it is, we can describe its properties. Here we have very little information when we measure something indirectly. We have very little information on what it might be. So this is a picture showing scientists trying to describe something without actually seeing it by having little information in it. So there are many, many different theories that could describe a discrepancy, such as the G-2 discrepancy. But we need more information to know really what it is. So we absolutely need the giant high energy machines also. So that is the end of my talk. Thank you very much for your attention. Let me know if there are more questions.
Sure, and thank you so much for giving this talk to us. In the interest of time, there's a couple of unanswered questions related to your talk that are in the chat. We haven't had anyone ask any questions live, so that we can get to Anna's tour. Is it okay if you answer those questions in the chat for people? I've been keeping track of them.
Sure. Can I answer? Can I answer in the chat?
Yeah, absolutely.
Okay.
Yeah.
Great.
Okay. Awesome. And I'll go back through once Anna gets started, and I can copy and paste any that were from further back. So awesome. Thank you so much. All right.
Thank you, Anna. I'm so sorry for taking a little extra time. Listen to Anna now. She's going to give an excellent tour.
Yes, and so I want to welcome Anna Driuti to our program. She is going to give us a virtual tour of the muon G-2 experiment. And so I believe you're able to share your screen now. And if you have any questions related to the talk again, feel free to put those in the chat, and Manolis can answer those for you. So I'll turn it over to Anna.
Thank you, Amanda. So welcome to the virtual tour of the G-2 experiment. My name is Anna. I'm a postdoc at the University of Kentucky. So before starting to actually virtually enter the building where the experiment is that you can see in this picture, I just would actually call a couple of a brief introduction to the experiment. Manolis did a lot of it, so but I will just give you I will just say a few words about. So the objective of the G-2 experiment is basically to measure a property of a muon with high accuracy. What's a muon? Muon is a particle, is a subatomic particle. We can think it like the heavier cousin of electrons. So it's about 200, muons are about 200 times heavier than electrons. So we actually experience muons in our everyday life. So I don't know if you're familiar with cosmic rays. There are particles that came from the cosmos, all over from the cosmos, and then they hit our atmosphere, and they start interacting with the particle in our atmospheres. And what happens is the result of this interaction are some secondary particles that reach our surface on Earth. And most of these secondary particles are actually muons. So while we are here speaking about science, we actually have about 100 muons that pass through our body every second. So we don't see them, we don't feel them, but we actually somehow have them in our life every day. So a muon also has an internal magnet, and is like a sort of miniature bar magnet, and also has an angular momentum. Manolis described it, we call it spin. And you can imagine the muon like a spinning top, or a spinning top. So the property that we are interested of is called gyromagnetic ratio of the muon, and basically we label it as G, and this G is actually the name of our experiment. G, Manolis already showed you some formulas, is basically an indication of the strength of the magnet and also the rate of the magnet gyration. So why we would like to measure this quantity. So this quantity is very important because as Manolis just showed you, we have a model for that particle physicists use, which is called a standard model of particle physics. And this model explains most of our experiment, but there are still some things that we observe in nature that we cannot explain with this model. Things like dark matter or like dark energy. But not only, also, for example, we know that at the beginning of the universe, matter and antimatter were more abundant, but now we only see matter. So why this is happening? We don't have an answer. So one way is to try to understand if there are forces or particles that we don't know about, we still didn't see yet. And one way is to try to create them by smashing atoms together, like colliding protons at big colliders, like the one at CERN or the one that we had here before at Fermilab, the Tavatron. But another way, another approach is the one that humanist uses, is like to actually check for the consequences of this interaction with these new particles. It's like, for example, if you have if there is a windy day outside and you see, actually, you don't see the wind, but you actually see that the trees are bending. So, and you can actually, if you have a little bit of formulas on how to describe the action of the wind on the tree, you can actually predict how much the tree will bend. But also by your, if you look outside the window and you take a measurement of this, of how much the tree is bending, you can actually compare your prediction with your measurement. And if there is a discrepancy, it means that in your prediction there is something missing. We do more or less the same. So we try, but with particles, we are actually measuring G, and we are looking at what the value of G, but also the theoreticians tell us what should be if we use all the particles and the forces that we know up to now. And so by doing this comparison, we actually are able to understand if maybe there is more physics. So let's switch a little bit and talk how actually we measure, we experimentally measure G. So the first thing that we need is a beam of muons. We need an abundance of muons, and we are lucky because here at Fermilab, there is a fantastic accelerator complex that will provide us muon. I'm gonna show you some picture of the aerial view of Fermilab. And so, sorry. Okay, so here you can see Fermilab from the sky, basically, and all the lines that you see here are the beam lines where our beam is circulating. The old Tavatron now is off, but we still have the main injector and the LINAC and the booster. And let me show you a very nice a very nice animation of all the particles all the beams that we generate here at Fermilab. So we don't only generate muons, everything starts with the proton source that it's near the Wilson hole, if you're familiar with Fermilab site. This proton source starts and it's accelerated in a linear accelerator, and some beam is used for neutron beam. Some instead goes to low energy protons that are accelerating in the booster. And this is actually used and delivered to the low energy neutrino experiment. Part of it actually start going around this big delivery ring and is making muons that are delivered to us. And I'm going to show you soon what we do with muon beam. Part of the beam is used to high energy neutrino experiments. And part goes over to the test beam facility. So as you see, there is a lot of complex, and we have a lot of kind of beams. But let's go back to our muon beam, what we do with our muon beam. Here. So once we have some muons, these muons are actually sent to us in MC1, and in MC1 we have a huge 50 feet huge muon storage ring. This muon ring is able to provide a magnetic field inside, and when the muon arrives, we have them all. They all have their spin oriented in the same direction, and they start circulating inside the muon storage region. While they are circulating inside the muon storage region, because their spin also precess. They are like basically the spin, the angle of between the spin and their momentum is changing, and we are very interested on this precession of the spin, because this is a direct consequence of the difference between G and 2. So it's exactly what we would like to measure. Unfortunately, we cannot measure it directly on the muons, because also the muons are also unstable particles. So they basically die after a few milliseconds. And so what happened is that when the muon dies, it creates two new particles. These new particles are the electrons and the neutrinos. We don't care much about the neutrinos because we let them escape our experiment. We actually are very interested on the electrons because we are very lucky. The electron basically carries the same information about the spin of their parents' muons. So by just looking at the spin of the electrons that came from the muon decay, we're able to understand we're able to measure basically the anomalous magnetic moment of the muon. We actually need also to know very well and very precisely the field, the magnetic field that these muons experience. So as I was saying, we have this storage region that, storage ring that provide the magnetic field. Let me go back to our building. So if we enter the building, this is the experimental hall, and you can see here the storage ring that in which we store the muons. If we just zoom over here, this is the last part of our accelerator complex. These are the last magnet that carry the muon beam inside our experimental hall. And then if we turn around the camera, we can see our ring. Let me go back and, oh, sorry. And show you it from the top of the, sorry about that. I clicked the wrong one here. So, okay, so the muon beam arrives inside our experimental hall from here, and then what happened is that they first see this huge ring. The ring actually wasn't built for this experiment. We borrowed the ring from the previous experiment. This was a big project. It happened in 2013 when we had to move the full ring from the Brookhaven National Laboratory in New York all the way down here to Fermilab. So the ring is very, we have to do it very carefully because the ring needs to be moved all in one piece, and so we cannot disassemble it. And also, it cannot be twisted for more than 3 millimeters. So that what we call the big move, as I was saying, happened in 2013 and has been done half by truck and half by boat. Let me show you a few pictures about that time. So here it is. It was a big journey. Part of it was done by boat, circumnavigating all Florida, all around Florida. And then part of it was done by going up through the Mississippi River all the way down to St. Louis. The last part of the trip was done by truck here in Illinois from St. Louis to Chicago. It takes about 35 days to bring the magnet all the way down here. So let me just give you a quick description of the magnet. Here you can see a picture when we were building the magnet inside our experimental hall. It's about 50 feet of diameter. It's made by steel. He is made by steel, aluminum, and superconducting coils. So the field that is able to provide is 1.5 Tesla field is more or less like the same field that you experience in MRI. And also is C-shape. This is very important because this C-shape is helping us. Here you can see basically a section, like if you cut the magnet in one of the points. The C-shape is very important because it allows the positrons or the electrons that are created when the muons die to curve and the inside part of the ring where we have all our detectors. An important feature of this ring is that the magnetic field that it provides is very, very accurate. So this is done by using a lot of instrumentation, active and passive instrumentation, like the wedges, some edge shimming, and some surface coils. When we use all this instrumentation, so without using all this instrumentation at the beginning, when we just start having the magnetic field inside the storage region, you can see here in the red line, we see a lot of variation around the ring. Like you have to imagine here to go just all around the ring. And after, when we start to apply all our corrections, we were able to provide a very stable magnetic field through all the ring, and it's the blue line that you see here. So you see that there was a huge difference after we were able to basically apply active and inactive material to the ring to make sure that the magnetic field was constant. Once the particle, let's go back to our. So once the particle entered to the magnetic ring, they have to, they see the first, oh, I should show you the pictures. Sorry. It's easier on the live on the room. Sorry about that. And so when the muon beam arrives and needs to enter our storage region, we have a device that is called infractor that basically provides the opposite magnetic field that there is in the region. In this way, the muon beam is able to enter the ring, and it actually doesn't have exactly the right trajectory to be in the center of the storage region, but is about 7 centimeters off. So in order to move the beam back to the correct trajectory, we use something called kicker. That are basically 3 systems that provide magnetic pulse, and they are able to move by the beam in the correct trajectory. Once the beam is in the correct trajectory in the middle of our storage region, then we use electrostatic quadrupole to squeeze the beam exactly at the center. Here you can see a picture of the inflector, a picture of the kicker, and a picture of the quadrupoles. The quadrupoles are in 4 locations around the ring. Finally, we have some devices to collect the positrons and basically measure their energy and the time of the arrival. And these are the calorimeters. Let's go in the center of the beam, and we have 24 stations of calorimeters. Here you can see 3 of them. They are all around the ring. Here there are some more. And the calorimeter basically are the instrumentation that is sensitive to the electrons and is able to see when the muon decays and what is the energy of the electrons daughters. The calorimeters are made by each of the calorimeter is made by 54 crystals. And here you can see some of the picture of the crystals and the calorimeters. These are the lead fluoride crystals that are actually then installed in the calorimeters in rows of 9 crystal and in a grid of 9 times 4 times 6 crystals. So there are 54 crystals at the end in the calorimeter. Here you can see also the back end of the calorimeter with all the instrumentation. Each crystal has electronics attached on it. We use silicon photomultipliers. Basically, when the electrons goes through the crystals, the crystals basically emit some photons. These photons are collected by our silicon photomultiplier, which they transform the photons in electrical pulses. Here you can see an image of these pulses. Here, for example, there are 2 positrons that hit the calorimeter, and you can see the first and the second. And on the x-axis there is the time, and basically the area of these pulses is proportional to the energy of the particle that hit the calorimeters. We also have another station that is able to actually look at the position of the beam, and these are the trackers. Here you can see a picture of the trackers. The trackers are made by straws, aluminum straws, and here you can see some of the straws. And when the electron goes through the straws, basically there is an electrical impulse inside, and we are able to collect this and basically know where the position where the electron has been created. So we can also go back and look what exactly a muon experience when it travels around our ring. Sorry. So this is basically both the simulation and reality of what happened when a muon actually is traveling inside the G-2 ring. So this is the simulation. You can see that the muon is basically staying in the middle of the storage region and see the trackers. So we saw the straws of the trackers. But we also are able to put a camera inside and look at the various parts of the actual detectors. This is really the actual storage region from real. So here you can see the quadruples. So I have to say that this simulation wasn't made by me, but we have actually a very active collaboration. Here is a picture of the G-2 collaboration. You already met Manolis. We are about 200 people from different parts of the world, some from Europe, some from China, some from America. And so, as Manolis already said, we are trying to, we are analyzing our final data set, our first data set, and we are hoping to have a result about this important measurement very soon.
Thank you so much. That was great. I love that video. It's like the 3rd time I've seen it, and I love being able to see the inside of that. That's so cool. So again, in the interest of time, if you have any questions about what you saw on the virtual tour, if you can put those in the chat, and Anna can answer those. She's also going to be part of our panelist discussion, so feel free to ask her questions as part of the panel. So I'm going to ask our panel of experts. We've got to turn their cameras on. We've got, I see Ketvan. We've got Jacob and Aisha joining us. Anna was going to be part of the panel of experts too. Manolis, if you want to, I know there's some unanswered questions for you. So I'm going to go ahead and have everyone introduce themselves. This is, just for our audience participants, this is very informal. In the actual Ask a Scientist, we do our tour and then you'd get a chance to kind of like walk around and mingle and ask people's questions. So that's what we're kind of trying to recreate here. So please feel free to ask questions about Fermilab related to their jobs as I introduce them. And then I have some, questions that people actually emailed me in advance. I have some Saturday morning physics students attending, so they actually sent me some emails of questions that they might want to ask but didn't necessarily want to ask live. So I'm going to go ahead and introduce Aisha. She is an engineer at Fermilab. If you want to, I looked up and you've worked on a lot, so I couldn't possibly summarize that. So if you want to introduce yourself.
Sure. I'm Aisha. I've been at Fermilab for almost 20 years. I've been in the accelerator division, more specifically the instrumentation department, which means I get to work on the diagnostic equipment that basically makes fundamental beam measurements and, intensity, position, profile monitors. And these will be installed all throughout the accelerator, from the source through the LINAC, through the booster, main injector, recycler, transfer lines, all the way down into the muon and other experimental facilities. So because of that, and because I've been at the lab for quite a while, I've kind of gotten my hands on all different parts of the system, and it's always been very interesting. It's never a dull day, and the science is always growing, always changing. So just when you think your design is done, they want you to revamp it, and it's a great environment for design and for learning.
And next, I'll introduce Ketvan. Ketvan actually works in our Office of Education and Public Engagement. She manages our exhibits. If you follow us on Twitter, you see quite a bit of her content on there. She's also a professor at Aurora University. So Ketvan, if you want to introduce yourself.
Sure. Hi, my name is Ketvan. I will not say my last name. You can pronounce it anyway. So just like Amanda did, I work for Fermilab Education and Public Engagement Office. I create exhibits that communicate Fermilab science, and it's a lot of fun.
And we have Jacob with us. Jacob is a main control room operator. So that animation that Anna showed you in the virtual tour, he is one of the people that makes sure that that all works as it should. So Jacob, if you want to go ahead and introduce yourself.
Yep, I'm Jake. I've been at Fermilab for a little over 2 years. Like Amanda said, I'm one of the accelerator operators, so we keep the complex running and monitored 24/7, 365. Make sure everything is running efficiently and safely. So we're responsible for keeping an eye on all the kind of electrical, computer, vacuum systems, where the particles are going, as well as clearing out the tunnels to make sure nobody's in there when we start powering on some of the strong magnets, and also sending particles through there.
And then Anna, you met, but I didn't know if there's anything else you wanted to say. Oh, you're muted.
So my name is Anna. I'm a postdoc at the University of Kentucky. I'm working for G-2.
And I want to give a shout out to some of Anna's family that is joining us from Italy. So thank you for joining us. Okay, so why don't we go to some questions? Let's see if there's any. If anyone has any questions, feel free to put them in the chat. If you want to ask them live, feel free to unmute yourself. Someone asked if you are interested in a doctorate in physics, what is the best undergraduate degree to get? If anyone wants to, Ketevan, do you want to take that one?
Could you please repeat the question?
Sure. So it says, if you're interested in a doctorate in physics, what is the best undergraduate degree to get?
Best undergraduate degree to get.
Mm-hmm.
If you are interested in doctorate in physics, the undergraduate degree is master, I believe.
Yeah, bachelor's or master's degree. Yeah.
Bachelor's or master's, but to do PhD in physics in any area, I believe you have to have a master degree in physics. And if somebody knows differently, please feel free to correct me.
Doesn't look like it. There was oh, go ahead, Jacob. Sorry.
So I believe you can have just your undergraduate and go right into a PhD. I think typically they look for physics bachelor's, but I don't think that's exclusive. That being said, I have physics and astronomy degrees. I don't have a PhD in physics, but that's from what I've looked and when I've talked with people, that's roughly the path that they've taken.
Great. Jacob actually had a question that someone had sent me earlier for you. So what is like kind of a day in the life like for someone running a particle accelerator?
It varies day to day. If everything is running smoothly and the experiments are getting all their particles, it can be pretty relaxed and quiet, kind of just keeping an eye on all the different systems. But more often than not, one component or another might break, or there might be issues. So we are kind of like the first responders for the complex, trying to figure out what went wrong. So sometimes there might be issues with like a pump that's trying to keep the pipe that the particles go through under a nice vacuum. There might be issues with that, so we can try and reset that from the control room. Other times we have to go out into the field to try and see if we can fix things that have turned off or broken. Other times we'll have to go down into the tunnels to see what issues might be. So it kind of varies day to day. And with us too, since we keep an eye on everything literally all the time, we work rotating shifts. So we work sometimes the days 8 to 4, sometimes work the evenings 4 to midnight. Other times we work the nights, midnight to 8 a.m. And then we also work on the weekends. So right now I'm off, but there's a crew in the main control room right now who has been there since 8 a.m. and will be there till 8 p.m. Today, looking at stuff and keeping an eye on the complex right now.
Awesome. And then also, Aisha, I had someone, one of my Saturday morning physics students ask a question about what's like the hardest engineering challenge you've had to solve? I know that's like a really big question, but if there's an example you can share.
So, I have my bachelor's in electrical engineering, and back when I graduated, the movement was just, people were just starting to program on FPGAs and controllers and doing embedded programming, right? So, and I was working with more IP stuff and more, automotive systems. So for me, the first thing for me was just learning about physics. So one thing about Fermilab is doing the engineering, you can't do it properly without understanding why the physicists need this measurement or how the device works. So understanding how electromagnetics plays and how it affects the beam shape and size affects how I approach the project. So from the beginning, it was always very challenging to design a system because it's no longer a black box. I had worked in the industry for a few years, and everything was a very, here's a really well-framed problem and how it fit into a bigger system. The experiments are new. They change, as experiments finish, new ones start, and they evolve from one to the next. So you really have to get a good idea of the big picture every single time a new project starts, because that affects how you design, because I'm not now constrained to my little black box. I have to see how it interfaces with every other aspect of the experiment. Right now we have, the flagship projects, PIP2, G-2, Dune, and those are pretty much pushing the requirements that we've had in the past in terms of power, in terms of how much data we're pushing in a real-time basis. I know in industry, we're talking 10 gigabit stuff real time, but that's not real time feedback systems. Those are real time in seconds, real time in milliseconds. Our systems that manage the beamlines need to be able to react on sometimes microsecond levels. That means we got to push, megabytes of data, get them processed, correlated in time. So each beam pulse that goes through, we have all the measurements go all together, and we're not mismatching things, and package it to the experimenters, to the operators, so they don't missteer the beam or cause an accident. And that's quite a bit of bandwidth and quite a bit of processing to do on a microsecond level. So now that's the challenge that I'm facing with now, is that we're taking very standard philosophies and trying to push our hardware and our control systems to be able to manage that. We have to upgrade. There's a big modernization effort on all the electronic boards and digitizers, as well as the actual control system that's in place. That it's very exciting. One thing about working at a national lab is that there's really no solution out there. It's a real design problem. So a lot of times you simulate and you propose things, and you got to do 2 or 3 iterations because, oh, you didn't realize this was going to be a problem, or something you thought wasn't going to be a problem actually ended up being the real bottleneck in the system. And because of that, if you like to solve puzzles, this is a great place to be for an engineer.
Awesome, thank you. We have a question from Dan that says, Manolis mentioned that the results of the G-2 experiment will be available in a few months. Do we have any idea on the outcome? Is it going to be far from the theoretical calculations?
So actually, we don't have an idea of the result because we blind the result. So basically, we apply a layer of uncertainty on the results, so we are not biased. This is very important because otherwise we will, we will try to see stuff that we will try to get through a result that maybe is not the right one because we were working through what we think is right. Instead, like this, we have no idea, so we cannot say anything till the last moment.
Awesome, thank you. I have a question from Corbin that I'll give everyone a chance to answer. Ketavan, I'll start with you. He says, I have a question that's unrelated to lecture. It's about what your average day at your job looks like, what kind of hours, basically asking about your path to Fermilab. So how did you end up coming to Fermilab? What degrees you have, kinds of classes you took. So Ketavan, if you wanna start.
Sure. This is a great question. I'm from Georgia. I was born in Georgia. This is a small country in Eastern Europe. And I got all my education in Georgia, master in physics and then PhD in particle physics, and worked for Alice experiment at CERN before I moved with my family to the United States. And I moved to the United States in 2002 with my husband, Guram, who is a physicist that works at Fermilab as well. And this is how I got here. And this is an amazing journey and the most exciting place to be and work. Fermilab. And what I do at Fermilab, at that point when we moved to United States, I decided to switch to education. I always was involved in education at some level, but switched to education, and now I work for Fermilab's Education and Public Engagement Office. Like I mentioned before, I create exhibits with my team, my colleagues, which communicate Fermilab science. And it is quite a challenge and exciting job because Fermilab science is so deep and so fundamental, and to create something, some kind of hands-on activity which would communicate this science and make it accessible and understandable is quite a challenge, and at the same time very exciting job. So we do that with a lot of passion. We create exhibits that are interactive. And at this point, unfortunately, Lederman Science Center is not open for public, for understandable reasons, but we have created a lot of virtual materials, which you can see on our website, virtual exhibits, educational videos, and stuff like that. I hope that answers your question.
Yeah, that was great. I love hearing about your journey. Jacob, if you want to go next.
Yeah, so I got my bachelor's in physics and master's in astronomy. And then after that, I was burnt out of school, so I came to Chicago and worked at Museum of Science and Industry here for about 6 years doing science education, which was a lot of fun. And then came to Fermi, seemed like some very cool hands-on, more technical work. And so, like I mentioned before, as an operator, we pretty much keep an eye on stuff, keep things running smoothly. If stuff breaks, we try and fix them. If we can't, we call experts like Aisha to help us fix stuff if we can't. And I think just also in terms of other operators, though, the bachelor's or a master's isn't necessarily required. We have people who don't have bachelor's degrees in physics who are still very good operators. Effectively, if you like technical challenges and like working with people, then it's pretty much a good match for operations.
Thank you. Aisha, if you want to go next.
So I'm gonna risk giving away my age, but I'm a product of MacGyver, basically. Very early on, I knew I liked math and science, but as you all know, that field is huge, right? So, but growing up with a few episodes of MacGyver, you really realize, look, I like to solve problems. I like to work with my hands. I like to put things together. And so in high school, I just basically tried to take every science class I knew so I could figure out what kind of engineer I wanted to be. I did poorly in chemistry. I did poorly in biology. So those were out the window. I really liked, mechanics and electromagnetics, and that sort of put me on track for electrical engineering. Learning about the work at Fermilab has been really insightful. When you look at Fermilab, you see it as a physics institution, and you sort of don't understand the amount of engineering that gets to be there, and but it needs to be, and that was exciting to find, and it's actually been a gold mine to work here. The hours are pretty flexible. There are core hours, but that's because we do a lot of collaboration. So people need to know when you're available and when they can expect you if they have questions. So that's pretty much how I got to Fermilab, and I've been happy working here.
And Anna, if you can finish up this question for us.
Sure. So I'm from Italy. I have a master's degree in physics, in particle physics, and a PhD in math and physics. I did my PhD thesis analyzing the data of the CDF experiment. So I start working, collaborating with Fermilab during my PhD. And after that, I started working as a postdoc. Right now I'm at the University of Kentucky, and I did my postdoc working on G-2 experiment.
Awesome. And we have a kind of a nice follow-up question from Zach that's asking, how and when did your interests in your subjects or line of work start, and what did you do to pursue those interests? So Ketevan, we'll start back over with you.
Okay, thank you. This is a good question. In high school, honestly, I didn't know exactly what was. In fact, I had different interests, but I would not say that physics was my top interest. But I had a great teacher in my last high school class. It wasn't called in Georgia senior year, but it is somehow similar to that. Had a great physics teacher, and I still think that teachers can make so much difference in our life, and that made me interested in physics, and particularly in particle physics. And this question of what is the most fundamental and building block of matter became somehow the center of my interest. And then I started reading about this. I remember my first article about particle physics. Most articles, most papers in particle physics are in English, and I didn't speak any English at all. I don't speak English even now, but it was even much worse. So I started with a dictionary next to me and started translating that. So it became kind of obvious to me that that was my interest. So I pursued this career in particle physics, but always was interested in education. Even when I was working in Georgia in Institute of Physics, as a researcher, I was teaching at the same time. And when we moved to United States, I teach part-time since we moved here. So yeah, somehow this combination of learning and teaching, and I love learning new stuff. Even now I read a lot, and sharing it with my students is a pleasure of my life.
Awesome, thank you. Jacob, you want to go next?
So I think for science-ish in general, it's been for a long time. Similar to Ketevan, it's kind of having great, for me, chemistry teachers in high school. That really got me inspired. In college, I kind of bounced around the sciences, starting in biology, and eventually found my way to physics. And that was pretty cool. And I've still even kind of bounced around as to what what subjects interest me right now. I'm kind of leaning more towards the engineering side of stuff. So trying to pursue those, just finding, in terms of, I guess, how to pursue those, I just kind of bounced around different jobs or majors to see how I like it. So work in progress, but in general, science and technical stuff has been for a while. But what specifically, I don't know, it's changing.
Awesome. Aisha?
Well, you already know my MacGyver background, but I would have to say that as I've been coming up, since I graduated from college, one thing that I realized is I really like to stay technical and have sort of the flexibility to really do real R&D development work. Not to say that we're not inhibited by normal money constraints and that sort of thing. But Fermilab is a really good balance of academia and R&D. And you're always learning something, and you're always getting to design something. One thing that I've also noted is that you really shouldn't take an opportunity for face value. There's a lot of silver lining in reaching out and meeting new people and in different opportunities. I learned about engineering at Fermilab actually through a friend, and it was through a non-related function. And because of, trying to be, have multiple interests outside of STEM, you get to meet people as they are and see opportunities that you may have not been realized that they're related to your interests at all. So I would just keep that in mind, that if you want to still pursue STEM, it's really good to be, have exercise the right side of your brain because you might meet people and see opportunities that you wouldn't have realized that they cooperate with the left side of your brain as well.
Great. And Anna.
So at school, I really love math. I was really thinking that I would be a mathematician in my life. But a few months before the end of the high school, they took us to see a tour of a low energy accelerator that was near my high school. And I basically fall in love for physics. And I was like, oh, I really like the creativity, the way that, not that math is not creative, but like I was really in love to see all these particles going around and thinking all of these things. So I decided to start to take an undergrad degree in physics. And I have to say my parents weren't very happy. They really want me to be an engineer. But I really loved that, and I started doing that. And then I was very lucky at the second or third year of my undergrad. I had the opportunity to come at Fermilab for the summer student internship. And since then, I fell in love for Fermilab. I love learning about new things every day, interacting with people with different cultures, different backgrounds, and working in teams. So everything at Fermilab was just like what I really liked to be in when I was gonna be a holder. So, and then I start my master in physics and then my PhD, and so and now I'm here.
Fantastic. I haven't seen any new questions in the chat or any hands raised. So I think I'm going to pose this kind of final question to wrap things up. So what is like if there's like an experimental result you're looking forward to seeing the most, if there's a project you're looking forward to seeing come online, what kind of most excites you right now related to like Fermilab science and the work that we're doing? So I'm going to kind of go in reverse order this time. So Anna, if you want to take that one.
Well, I cannot, I have to say G minus 2, sorry. We are really waiting for this result. And we are actually just starting our run 4. We started a couple of days ago. So we are really looking forward for this result. It's been a long journey. It's been a lot of good times. So yeah, we really would like to see that result.
Aisha, if you want to go next.
Yeah, sure. So right now, artificial intelligence is one of the biggest initiatives at Fermilab, and we recently got a couple $1 million grant to do get a project underway to fold that into the FPGAs and help with some of our loss monitoring systems in the main ejector and recycler. So that is, especially at Fermilab, it's a very new thing, and it's been done at smaller labs. So it's quite an undertaking, and it's quite a short timetable compared to some of our other projects. But it'd be very interesting and very helpful if we can optimize systems using our artificial intelligence.
Jacob?
I think seeing the new experiments, how they're going to incorporate into the complex. So when PIP2 comes online, the new beginning of the accelerator, when the Muta-E experiment gets up and running, when the DUNE experiment or long base 9 neutrino facility gets up and running, seeing how that all fits in with everything else that's already running, I think that'll be pretty cool.
And Ketevan, I'll leave it with you.
We all are very excited about muon G-2. I have to mention that, and really waiting for the result. But also we, I mean, our office are closely watching all Fermilab experiments, current experiments, and future experiments. We are excited about June, of course, and waiting for the next supernova to be detected by June detectors. We are excited about Mu2 results, and of course, quantum computing, and everything that's going on is extremely exciting, and physics beyond standard model is super interesting. So yes, we are really excited and interested in what's coming next.
Well, thank you all so much. You know, this concludes our virtual Ask a Scientist. I want to thank all our participants for joining us. Thank Manolis, Anna for doing the tour and also being a part of our panel of experts. Ketavan, Aisha, Jacob for being part of our panel. I really appreciate that. So I put the link in the chat. The next virtual Ask a Scientist, the telescopes we build for cosmology, takes place on January 10th. It's also a Sunday at 1 p.m. You can also get to our registration directly from ed.fnal.gov. And also it'll be on our Twitter and Facebook accounts. So make sure you follow us on Twitter at FermilabEd. And again, thank you so much for being here for the launch of this virtual program. I really appreciate you spending your Sundays with us. And I look forward to the next virtual Ask. So thank you all. Have a great afternoon and rest of your day.
Thank you.